the values of wellbore pressure, and you can convert those to, this is, we didn't talk much about this in class, but this is specific gravity. That will be the SI version of pounds per gallon. And here you have the values in pounds per gallon. And here's the summary of the results. As pore pressure increases, you expect to have your mud window to decrease, right? Let's see. These are all the numbers. Here's a plot, which is a little bit more interesting to look at and to compare the results. So if your lambda p is 0.44, this is the result for PWBO 70 and for PV. This is your mud window. As lambda increases from 0.44 to 0.60, we can see over here that, as expected, the PWBO is going to increase and your PV is going to go down, and that is because you are lowering the effective stress on the rock. If you lower the effective stress on the rock because you're increasing the pore pressure, now your rock is weaker. If your rock is weaker, your mud window is going to be smaller. So you get to a point that even here the value of PV and PWBO, they cross each other, and at this point you may even have like a negative mud window, which means that you wouldn't be able to drill that wellbore under those conditions. Let's see the second part of this problem. Yes, Mr. Awan.
What's the practical way to drill through something if it doesn't have if the mud window is negative, like in real life? How would they do that?
Well, you may want to do it like very quickly. So you just drill and then you case it right away. That's, for example, a solution in salts, salt formations, that the wellbore closes right away, so you want to drill and case it. And another solution could be to increase the strength of your rock. Some people would inject some sort of polymers and harden with time to make it stable. Second part of this problem is about interpreting a stress map and interpreting that stress map to get to know what will be the orientation of the breakouts and tensile fractures. And in this case, what you had to do was to go to this world stress map, and let's look for North America in this case. North America stress map, and out of this map to interpret what is the orientation of horizontal stresses. In these maps, you always, these arrows are going to tell you what is the orientation of horizontal stress. Okay, that's very important to remember. It's not minimum stress, it's always horizontal stress. Of course, we wouldn't be able to see here vertical stress, and that, well, it doesn't matter either, right? But remember, this is not plotting S1, it's not plotting SH mean, it's always plotting the direction of SH max. So that will also be the direction in which you expect that you have your compression tectonic stresses, right? So if SH max, for example, here, Niger Eagle 4, it's in this direction, you expect that there is a compressive tectonic strain in this direction. Important things about these maps. Again, as I told you, is to interpret what is the orientation of SH max And based on these kind of maps, you could also tell right away what is the orientation of wellbore breakouts, of tensor fractures, and the expected orientation also of hydraulic fractures, if you were to do hydraulic fractures, right? Let's take a case. This must be an old map, because by now there should be a lot of data over here. Let's go here to the Permian Basin. What do you think is the orientation, or let me ask you, in which direction would you drill horizontal wellbores for hydraulic fracturing in this location? And this is, I can tell you it's normal faulting. So you have to tell the driller in which orientation to drill these wellbores. What would be the azimuths of those laterals? Here in the Permian, where I have the mouse.
Like 60?
60 to what? 60 like clockwise from the north?
Yeah.
Like that? Are you sure?
70 or 80?
So 120. 120 like this. So remember this SH max, okay? In normal faulting and strike slip, your wellbores have to be in which direction for multi-stage hydraulic fracturing?
Perpendicular to SH min?
The hydraulic fractures are perpendicular to SH min, right? Hydraulic fractures are always perpendicular to S3, and this case will be SH min. But if you want that, your wellbore has to be in the direction of SH min.
Oh, yeah.
In the direction of SH min, right? So let me draw that quickly. So in this case, apparently something like this. That red arrow is SH max. This one is SH min. So if you want to have fractures that look like this, you need your wellbore to be drilled in the direction of SH min. In fact, many of these maps, as you can see in the legend over here, the information about the orientation of a state of stress actually comes from the wellbore itself. That's something that many times you do not know a priori. So in order to know in a specific location what is the orientation of a stress, you may want to take a look at the image of your wellbores. If you locate where the breakouts and tensor fractures are, that's going to give you a strong indication about the orientation of the far field stresses. And these maps, you see sometimes they are made with information of breakouts, drill-induced tensor fractures, seismicity, polarity, coring, hydraulic fractures, geological indicators such as faults or something which are called dykes. Dykes, we never talked about dykes, right? I think we have a little bit of time today to talk about dykes. Dykes are natural and giant hydraulic fractures. It looks like a good one. This is not a magmatic dike, but it's whenever you have pressurized fluid in the subsurface naturally and they overcome the minimum principal stress, they form these dikes. And sometimes you have these magmatic dikes that when the magma cools down, they just stay in place, and they are very cool to look at. Like for example, look at that. Those are dikes. Old hydraulic fractures of magma that had stayed there and have not eroded with time because the rock is very hard. and you can see it from on the surface or sometimes underneath the surface as well. Okay. Let's come back to here. In this case, you could interpret that SH max, as we saw in the map, was coming in this direction. When you look at these maps, I'm not asking about an exact angle, okay? I just want you to tell me more or less in which direction it comes from. And if you see many arrows more or less at different directions, just take an average of that. But in this case, SH max is coming at about 30 degrees from the east towards the north. And if that's the case, and this normal faulting, you will expect breakouts in this location and tensile fractures in that location. The other way that you could solve this problem is I give you the orientation and the azimuth of the breakouts. Tell me what is the far field orientation of the stresses. Okay. Any question about this problem? No? Let's go to the next one. Next one, it's about stress and isotropy. So here, what we want to do is consider a different problem. And now this one is mostly on SI units. I expect that you guys know how to go back and forth from SI to field units, okay? You can solve the problem in any system that you want. Just do it in the way that you find more convenient. But you should be able to provide the answer in both. Either if you do the conversion at the beginning or at the end, that's up to you. But you should know how to deal with the two unit systems. All right, so here we have far field stresses, properties of the rock, and in this case, the horizontal maximum stress is going to increase, and that's a variable that we're going to vary. Again, total stresses, pore pressure, effective stresses, properties of the rock, what are the stresses in plane, and finally, just apply the equations, and you obtain these values that then you can convert to specific gravity or to pounds per gallon. Here's a summary of the solution, and as what you get to see is that as you increase the stress anisotropy, so sigma h mean is always constant, but you're increasing sigma h max every time more. As you increase a variable, your mud window gets smaller and smaller. There is something very interesting here in some of these cases. Whenever your PB is smaller than PW shear, and also you're drilling at a PB, let me, wait a minute, I want to add something in there. Your pressure in your wellbore is higher than PB. If it's higher than PB, what would you expect? Yeah, but what kind of failure would you see in the wellbore? Tensile fracture, right? And if your PW is lower than your PW shear, what are you going to expect? Breakouts, right? But it might happen that in some conditions, like as in this example, that you may have a stable condition in which you have simultaneously both breakouts and tensile fractures. So in that particular case, you are causing both tensile fracture and shear failure around the wellbore. In a single experiment, you cause both. And the wellbore is still stable. And if you remember those images that we show about wellbore breakouts and tensile fractures, that was an example of that. It was an example in which you have simultaneously breakouts and tensile fractures. Usually this happens whenever you have a lot of stress and isotropy. Whenever that differential stress, delta sigma, it's significant, so that it causes a lot of compression in here and also tension in this location. And if, for example, we take a look at the mud window, in this case, this is the case for sigma h max and equal to sigma v, we see that this is what I was showing before. PW shear is over here, PB somewhere over here, and PWBO is in between those. So if you were to drill with this drilling mass density, you will have breakouts and you will have tensile fractures because it's above the value of PB. Okay. Any questions about this problem? Let's see how we're doing with time, because I do want to go through the exams. Oh, we don't have much left, so let me go a little bit faster in here. This offshore problem, it's very similar. Let's see, number 4. Number 4, this offshore. It's still vertical. I don't know why I draw this horizontal wellbore. But it's still a vertical. Okay, it was to calculate TVD. Remember that in all these problems, we want to calculate TVD, not measure depth. And you calculate your stresses, calculate your pore pressure, your effective stresses, you know the properties of your rock, and you can calculate again all those numbers. The difference here is that the way in which you compute your vertical stress. Remember that in offshore cases, your vertical stress is not just simply 1 psi times the depth. You need to consider the depth of the water. Otherwise, you're going to get a result which is not correct. And the last one, it's about a horizontal wellbore. And this horizontal wellbore, you have to consider 2 cases. A wellbore drill in the direction of SH max, a wellbore drill in the direction of SH min. This is exactly the same as with what we have done before, but now notice that the in-plane stresses, so this part is the same, SV, pore pressure, sigma V, sigma H min, sigma H max, but when you get to analyze every specific wellbore, the stresses in plane are not the same. So this is the case for a lateral in direction of SH max. This is the case for the lateral in direction of SH min. And again, you can calculate all these values, but notice that these values now are not the same. And let's see what we have in here. So this is a wellbore drilling in the direction of SH min, right? So this A. And this is a wellbore drilling in the direction of SH max. So this one is B. This is a case of, as we see over here, what kind of stress regime is this? Can you guys tell me? So I'll make sure you're still awake. Strike sleep, right? Strike sleep. So this strike sleep, then SH max is going to be higher than SV. Therefore, you will expect breakouts in that location and tensile fractures in this location. In this case, you will expect far away from the wellbore a reversal of the direction of the tensile fractures because of the same phenomenon that we discussed before. That far away from the wellbore, a hydraulic fracture will rotate according to the far field minimum principal stress. And in this case, this is strike slip, so SV is higher than SH mean, so you expect breakouts on the sides, tensile fractures on top and bottom. And then for the stereo nets, SH mean going to, in this example, to the south will be that one. SH max going to the east will be in that location. And this is the 3D version of that. And this is the block version of that too. All right? Okay. Any question about this problem? No? What do you want me to do? Go to the fault homework. Remember these two things, okay, that Jeffrey should have fixed by now. But they are, I uploaded my version in Canvas. Homework or tests? Tests? Okay. Nobody objects, so I'm going to go through the tests. (2016 or 2017? Where do you want to start? 16? Okay. Any questions about this part? No? No? Okay, I continue. Let's go to the problem. Okay, this is a typical problem of finding ideal orientation of shear fractures. And in this case, we have a normal faulting regime, right? So in a normal faulting regime, you will expect always these faults to be steep faults with strike that coincides with direction of SH max and with the dip which is equal to that angle beta. Stereo net projection. Always remember that, for example, if this is 1, a normal point to that is what will end up with this point over here. And this is number 2. A normal point to that plane, it will end up in that location. I expect that you are able, if I were to give you just that point, you're able to tell me what is the strike and dip of that fault. Okay? Notice that the strike is not where that point is. The strike is at 90 degrees from that. The point is there, but the strike of that fault is 90 degrees. All right? The dip is straightforward. But remember that this is dipping to the south. It's closer to the north, but it's dipping to the south. And this one is dipping towards the north, as you can see from that block diagram. Any question about this problem? No? Remember, faults closer to here, to this region, are the ones that are more likely to reactivate. This is a very nice problem. I like it very much. And it's an application problem. Those kind of problems, I expect that you use everything you have learned to be able to use that into a real application. So what we see here, this is a salt diapir. It's a salt diapir, and as it rises, it makes the sediments on top to kind of expand in this direction, but also in that direction, because these domes, most times they have a radial symmetry. And because this is expanding, that's sort of a negative tectonic strain. And as this expands, and with a constant vertical stress, if you're lowering the minimum principal stress, you cause faults in normal faulting. And those are those faults. So let's see, in this case, these are going to be normal faults because this is an extensional regime. And if you keep this, the overburden constant, it's going to be a normal fault. You're lowering a lot here the horizontal stresses. That's why you have those faults. And in many of these faults, particularly around salts, you can have oil accumulations. All right, so, and then what it follows is just regular business. You know the depth, and based on that depth, you have to calculate what is the expected horizontal stress. Notice in this case, the minimum value of horizontal stress is going to be limited by the strength of those faults. Even though and this is very important, guys, even though we have an extensional regime, as in this case, notice that even though if this is going in this direction, we'll never have here zero horizontal stress. That's not possible. And it's not possible because before that happens, you're going to have faults. But there's always going to be a compression. This is always under compression. And what is the value of that horizontal stress, which is, if this is a compression, is going to be the value of the vertical stress, effective vertical stress, divided by this friction and isotropy coefficient. And in this case, it's this number. And the dip of the faults will come straight out of the friction angle. And the last part is that you're looking from the top. And the salt dome, it's kind of circular. What you see here is a cross section. So it may be a cross section here, here. But if you were to take a cross section in this direction, you will also tend to see these kind of faults, which are in the other direction. So there is actually no real preference in some of these cases for where faults will occur. And the strike is not really defined in this case. And this case, it actually happens in nature. And in places where the two horizontal stresses are very similar, that leads to something which are called polygonal faults. And this happens a lot in the North Sea. So if you look, this is the same thing. It's an interpretation, but believe me that this comes from seismic images. You see the faults over there, but if you were to take a cross-section perpendicular to that, you will also see faults in that direction. And that's because the two horizontal stresses are very similar, so there is no actual preference for those faults just to be either in this direction or in that direction. But those are normal faults. All right, let's come back over here. And yes.
So if it was a reverse faulting regime,
Yes.
then essentially all the arrows in the picture would be flipped, right? It would be backwards.
Correct.
What would a strike slip look like?
Strike slip, in this case, you will have to see it from the top. And from the top, the arrows will be parallel to a horizontal plane. Yeah, good point. So it's such a good problem that I want to spend a little bit more time. You see how when this starts to fail, this block comes down to take the place of what it was here before. So this one goes left and right, this block goes down, and those are those arrows over there. And the last problem is a problem about wellbore stability, and this is a horizontal wellbore. First of all, always get your stresses right. Make sure you get your stresses right. And when you get your stresses right, just after you do that, you can apply the equations for PB, P shear, PWBO, or whatever, and after you recognize what are the stresses in the plane perpendicular to the wellbore. This is very important. If you don't use the stresses in the plane perpendicular to the wellbore, you're not going to get the right answer. In this particular case, we have a problem in which, let me see. No, this is not the one. It's the one in the other exam, that you have fractures. So if you have natural fractures, you may want to neglect any suggestion of what is the value of tensile strength. So here, just need to compute the breakout angle. And, okay. So here you have fractures. So drilling cuts suggest shale is already fractured. So if it's already fractured, your tensile strength is going to be 0, even though a small piece of shale do not have a 0 tensile strength. Any question about this problem? No? All right. So let's go to the other one. We have 10 minutes for that. Don't worry about this equation. This equation is about hydraulic fracturing, okay? That's not going to be in this exam. All right, so exam number 2. Stop me if you need any clarification about these points. No? This one? No? Something very important about this. Remember that the Kirch solution assumes isotropic rocks. And as we have said many times, rocks are not isotropic. So Kirch solution is just an approximation. And the equations that we wrote, PV, PW shear, all of those are based on the Kirch equation of isotropic rock. If your rock is not isotropic, Kirch equation is not going to work very well. All right, so nothing about that. I like this problem a lot too. Let's do a let's take a look at that map in real time. So the same as you might have these stress maps as the one I showed before, right? Where is the stress map? I think like that one, okay? We also have maps of wellbore surveys, okay? So particularly